Dear participants, welcome to Decision and the third International Congress on Human-Computer Interaction Optimization and Robotic Applications. My name is Emir Köksal. I have been working for the Department of Mathematics of 19 Mayıs University as Associate Professor Doctor in Samsun, Turkey. I'm the chair of Decision. First speaker is Forat Falih Hassan. The title of his talk is An Approach for Data Transformation in Homogeneous and Heterogeneous Information System. Ali. Ali. He's probably absent.
Hello?
Yes.
I am Forat Falih. I would like to start presentation.
Okay. I want to mention that the duration of the presentation is 10 minutes for each presentation, okay?
Okay, thank you.
You can start.
Thank you so much. Assalamu alaikum. Thanks for giving me this opportunity to present my topic, which is an approach for data transformation in homogeneous and heterogeneous information systems. My topic, as I titled, I'm going to present it. This is your presenter, Forat Falih Hassan. I am presenting for UUM, University Utara, Malaysia. I would like to start my presentation using a background about the topic. The background which focuses on the huge growth in data management systems as a result of rapid change in the technology of data storage systems. As the second point, data accumulated by information systems play an important role in many modern companies. So when we talk about different companies, we have to think about the transformation way. So companies occasionally transform their data between different information systems, either because of the customer demand or data technology change. So when that happens, the data from the legacy system has to be transformed into new systems. So as a background about this part, I would like to give the way or the method and the technologies about the transformation of data. The data transformation method between different information systems gets more complex day by day. So gradually, the data transformation or dealing with big data or metadata is going to be complex, and it is not as usual. It will be easy because of the change that can happens inside each method that you use to deal with the stored data in different systems. These complexities or sophisticated things in data transformation generate many issues related to the quality of data between the source and the target systems. So in this part, I would like to give some kind of issues and problems that can affect on the data transformation. So many issues related to data integrity and completeness has been shown recently in data transformation processes. So there are main 6 problems related to data quality that could be shown as in the transformation systems or transformation processes from the system to another. These data are, or these problems are going to be shown as data type mismatch, specification mismatch, missing values, typing errors, redundant data, and incorrect data values. These 6 problems or huge challenges are going to be inside data quality. So we always deal with these problems in order to try or to choose the approach that we can go over in order to solve some problems. A new approach must be taken into consideration to deal with the data transformation and management in compatible and incompatible data sources. Hereby, so when we say that, this means that to address data transformation from a system to another, this means that we have to get the middle of the system in order to make it interact with the source and the targeted system. So these the proposed approach are going to be starting from determining the requirements. Second, identifying the data source. And third, dealing with extraction and transformation and loading the data, or loading the stage of the data. This is the term that we call ETL, for extraction, transformation, and loading. Then we deal with the model information and model environment. And then we go to the second ETL stage, which is verification of the quality of the issues. Finally, we target database systems in order to get better results from dealing with data, with big data. So the 2 ETL stages are proposed. The first one to deal with the source systems, and the second one in order to deal with the targeted database system. So data quality issues can be addressed in data transformation processes, which increase the integrity and the completeness in the sharing data between different information systems. So as a result, we can conclude that the proposed approach can be a good information system, can have a better information system performances. It can minimize the issues related to the data quality in transforming processes. And finally, increases the integrity and the completeness in sharing of data between different information systems. And if in the future, as extension for the proposed work, and all the presented methods in this topic, with the algorithms under this research must be designed and achieved in the future. Thanks so much for listening.
Thank you very much for your presentation. Do you have any question, comment, or remarks? No question? So everything is obvious. Thanks again for your presentation.
You're welcome. It is my big honor. Thanks so much.
So now, next speaker is Gaetona Zarcone. The title of the presentation is Image Processing for GEO. He or she is present or absent? No. Fatima is present. The next speaker, the third speaker of this session.
Yes, I'm here.
Okay.
Okay.
Because of the fact that the second speaker is absent, so we are continuing from the third speaker, Fatima Noure. The title of her presentation is Enhanced Super Twisting Phase RISE Control for Trajectory Tracking of Parallel Robots.
Yes, I will start.
Yeah, you can start. Sure.
Ladies and gentlemen, hello. My name is Fatima Nouri. I am PhD student in the Robotic Parallelism System Embarqué Laboratory in the University of Science and Technology VROOM3, situated in Algiers, Algeria. We have the pleasure to present you our work about enhanced support twisting-based controller for parallel manipulator. We'll begin by an introduction. Then we'll describe both of the Velos parallel kinematic machine and the proposed control solution. After that, simulation results will be showed, and we will finish by conclusion. During the last decades, industrial robots have played an important role in industry. According to their structure, robots are classified into two categories, parallel and serial. Parallel robots are used in a wide range of applications, such as laser cutting, machining application, industrial robots, medical robotics, machine tool, pick-and-place applications, and so on. At present, parallel manipulators are being the most suitable robots for tasks requiring high acceleration and high accuracy. However, the control of this type of robots is challenging tasks. This is due to the nonlinearities which become more significant when operating at high acceleration, and also because of models' uncertainties. In literature, several control schemes have been proposed for the position control of PKM. These control schemes can be divided into adaptive and non-adaptive control schemes. In adaptive control schemes, we can find time-varying feedback rise control, nonlinear PID controller, L1 adaptive control, and so on. In non-adaptive control schemes, we can find the classic ID control, nonlinear PID controller, computer tone controller, sliding mode control, support twisting controller, and so on. Support twisting algorithm is the most second-order sliding mode algorithm. Support twisting controller generates continuous signal which has the merit of canceling chattering effect. In order to enhance the performances of the support twisting controller, we propose to replace the integral term of the support twisting controller by a rise control term. This choice is justified by the fact that the rise control technique is non-model based and has the potential to accommodate to a large class of uncertainties. This control method is well known by a unique integral term, which is based on a signium function, as shown here. It can accommodate a large class of uncertain and nonlinear systems like the class of parallel robots. Proposed control law is composed of two parts: an enhanced support twisting control term, which is responsible for rejection all disturbances, and equivalent control term, which is responsible for maintaining the system on the sliding surface. This is a block diagram of the controller. The proposed control law is validated in simulation using a 4-degree of freedom parallel manipulator called VELOS. VELOS robot is a 4-degree of freedom non-redundant parallel manipulator designed and fabricated at Laboratoire d'informatique, de robotique et de microélectronique de Montpellier for pick-and-place applications. VELOS robot is composed of a fixed base related to the moving platform through 4 identical kinematic chains. The moving platform can perform 3 translational motions along X, Y, and Z axis and 1 rotational motion around Z axis. In order to compare the performances of the two controllers, both of them are implemented in simulation, where 2 scenarios were imposed for evaluating the robustness of the proposed controller. In the first scenario, no additional mass is added to the moving platform. The reference trajectory chosen for the simulation is a rectangular trajectory as shown here. Errors in the Cartesian space are illustrated here. We note a good trajectory tracking for both controllers, but we notice a considerable rejection in the range of the error when dealing with the rise-based controller. This is due to the fact that the support twisting controller is control of any nonlinear system, but also the rise control term is responsible for remaining all handle almost all the remaining uncertainties. We should notice that the actuator limits are 127 Newton meter and minus 127 Newton meters. We can notice that the computed that the torques are in the range of actuator limits. In the second scenario, a payload of 2 kilograms is added to the moving platform, since Velos robot is designed for pick and place applications. So it is important to test its robustness toward payload variation. After adding a mass of 2 kilograms, we can the proposed controller toward payload variation. The enhanced super twisting controller ensures negligible errors comparing to the super twisting controller. In this presentation, the original super twisting controller has been enhanced by adding a rise control term in order to improve the tracking performance in terms of accuracy and disturbances rejection. The proposed controller benefits from the advantages of the super twisting controller and the rise controller. In order to evaluate the effectiveness of the proposed controller, simulation has been established using a 4 degrees of freedom non-redundant parallel manipulator called Velos robot. The results obtained in simulation showed that the enhanced super twisting based rise controller overcomes the original super twisting control in terms of accuracy and payload variation. The range of the errors resulting from the proposed controller were considerably reduced thanks to the features of the added rise control term. Thank you for your attention.
Thank you very much for your presentation.
Yes, you're welcome.
Do you have any question, comments, or remarks? No question? So everything is obvious. Thank you very much again for your presentation.
Thank you, sir.
Okay. Next speaker is present or absent?
Hello. I'm Nicholas.
Nicholas?
Yes. Can you hear me?
Yeah, I can hear you, but your name does not appear in the name of speakers in the program of decision. So could you please tell me the AD number of your paper?
It's 223.
Sorry?
2, 2, and 3. Development of a tomato harvesting robot.
2 to 3. So I think that your presentation is located in another session.
Can you tell me more details? Because I see the program here and I'm after Fatima Nouri, as I can see.
Second, I'm checking the other session, just seconds.
Okay.
2 to 3, right?
Yeah.
No, at this time, starting from 15, from 6:15 to 7:30 p.m. The number of your presentation does not appear in any session, unfortunately.
Dear Kuksal, dear Emir, can I speak?
Yes, sure.
Yes, my name is John Fasoulas. I'm a colleague of Nikolaos. If we go to the program, we can see that there is the presentation there.
Look, just a second. The name of the second speaker is Giatoni Zarkone.
Yes, of course.
So, so as a first, so we'd better continue from the second, by starting from the second speaker, but he's probably absent, right?
Yes, yes, yes. We can see that the
Next
name of
one. Okay.
Gaetano Zarcone is in the program.
Yeah, but your presentation,
Our presentation appears at the session 8.3, VROOM3.
8.3. Could you please tell me the AD number of your paper, please?
Yes, 223.
223 does not appear in the program of the session A3.
Where
Yeah.
we can download the
So
program?
you can download it from the main page of the conference.
Yes, but if we go to the main page of the conference and download, we can see that it is there.
No,
Can I share
right
the
now I
screen?
am sharing with everyone the program. You can check from right here. Bilal, just a second. So, Bilal Mustafa.
Yes, of course.
Mr. Appel, you are here. Just. So after the others speakers of decisions complete their presentation, we can communicate again. Okay.
Okay.
Can I start my presentation or wait for
Bilal, right. Next speaker is Mr. Bilal Mustafa. The title of his talk is IoT-based low-cost smart home automation system. Right, you can start.
Assalamu alaikum. Hello, everyone. I'm Bilal Mustafa from Superior College, Lahore, Pakistan. My topic is IoT-based low-cost smart home automation system. First one for the introduction. IoT is one of the most important 21st century invention. Today we are living in the world of automation and everything is going to be automated. The adoption rate of throughout the world is very high, and according to the researchers, that only in China, the number of IoT devices reached up to 24 billion in 2021. The basic goal of IoT is to build a superior world for humans. As shown in figure 1, you can see that IoT is used and implemented in different application domains, that is healthcare, agriculture, smart homes, smart space, transportation. In healthcare, the concept of the remotely controlled patients. In agriculture sector, the concept of smart agriculture, and that is automatically watering to the yields and plants. In smart homes, the home appliances, lighting, fans, air conditioning is remotely controlled by the mobile devices, and moreover, the safety and security system can also be installed in homes. In smart cities, the concept of the automated parking and smart street lights and transportation domain, the concept of autonomous vehicles. So in all domains, the IoT is very successfully implemented in all domains. Let's come to the topic, that is smart home. Smart home makes life simpler and more comfortable. Home appliances like air conditioning, washing machines, refrigerator, fans, lighting, remotely controlled with the help of mobile application. We can also control the home appliances via the desktop, laptop, smartphones, tablets by using various technologies and controller technologies like the Wi-Fi, Bluetooth, and the controller, that is Arduino or Raspberry Pi microcontroller. In addition, the security and safety system can also be installed in smart homes, which brings comfort and ease in our life. So the background is there are 3 types of home automation that was used in power line home automation system, wired home automation system and wireless home automation system. In power line home automation system, it does not need any additional cables for transferring data. The existing power lines used to send data, but it's quite difficult and old system and have significant complexity because for that purpose, the additional inverters and converters are required. The second one is the wired home automation system. In wired home automation system, we use physical cables like Cat5 and Cat6 for transfer and encode the information. The wired is used in new homes and as well as in the existing homes. Hard wiring is a good choice because wiring is reliable and can easily join all systems together. But it is quite old system because for existing homes, it is difficult to line cable from 0 point because may affects the appearance. So the third one is the wireless home automation systems based on wireless system. In this, basically, it is extension of wired automation system, and this we use the technologies of Wi-Fi, Bluetooth, Zigbee, etc. to control the overall operations. The different technologies that are used in IoT are the low cost and low power sensor technology. The different sensors that are available in markets are very low cost and they consume very low power. No need to replace batteries after regular intervals. The adoption rate of IoT is increasing day by day. And it is performed via the Wi-Fi, Bluetooth, and services of the internet and cloud computing. We use cloud computing because the sensors and devices used in IoT generates huge amount of data traffic. But these sensors have very little storage capacity and processing power. So cloud is used for the infrastructure and cloud perform the processing, connectivity, and storage. Different smart home applications that are discussed in the paper are the remotely controlled home appliances. With the help of that, we can automatically remotely control your lights and appliances. The safety system that is the fire detection system and the security system that is included detection system are used in the statement. The problem statement after deep learning of the literature review, of a deep study of the literature review, it was found that the smart home automation systems that are available for commercial purposes are still very expensive and that are unaffordable for the families of middle and lower class. So there is a need to develop a system which is cost effective and adaptable by the users of all age groups. In this paper, a cost-effective, user-friendly IoT smart home model will be presented with implementation that focus that system is reliable, affordable, and fulfill the needs of home users. The model is based on Arduino microcontroller that is used to control the overall operations. ESP Wi-Fi module. This is also used to control the operations for wireless communication. Flame sensors to detect fire. Motion sensor, that is PIR motion sensor to detect the unwanted suspicious activities. Relays that is used to turn on and off home appliances. Jumper wires to make connections. Power adapter, USB cable or batteries to provide voltage to the Arduino microcontroller. Blink app. The Blink app is used with smartphones. The Blink is open source and widely used in IoT applications and internet connection. The project includes three systems that are the remotely controlled lights, fans, security system, and the safety system. And this is the methodology. The remote fan lights, with the help of smartphone model, are able to control home lights, fans, and other appliances remotely through their mobile phones. For that purpose, Node MCU ESP8266 Wi-Fi module, 4-channel relay, or you can use any other relay, 2-channel, 1-channel, and up to 16-channel relay according to the requirement. Jumper wires for make connections, Blink app, and smartphones. For the site purpose security system, the included detection system. So the part of the paper, the presented security system detects the suspicious or unwanted movement and intimates timely or in case of emergency. For the said purpose, motion sensor, that's PI motion sensor, buzzer, and Arduino microcontroller is used. And in safety system, that is a fire intimation system that detects the fire or flame in house and intimate us timely by sending alert to our mobile devices. For that purpose, ESP8266 Wi-Fi module for wireless communication, flame sensor, and services on the internet with the Blink app is used. Experimentation. In the experimentation phase, the fire intimation system is basic need from appliances. yes, safety, brings satisfaction and comfort in our life. The system detects flame fire and intimate us timely by sending message or alert to our smartphones with the help of internet. Link app installed for the set purpose in our cell phone, which is configured by using the OAuth code. It is, I will tell you that when you are downloaded the from the Play Store or App Store, and you can make a new project, and that project then auth code is sent to you. That auth code is in our sketch for configuring the Blink app with our project. For the shared purpose, the system node and CS8665 Wi-Fi module, flame sensor, jumpers, power adapter, and Blink app are used. Node MCU Wi-Fi modules control the overall operations of the system. The sketch program is uploaded to ESP8266 Wi-Fi module through Arduino ID. It is important we must select the board Node MCU in Arduino ID before uploading the sketch. Arduino ID is the software that is used to transfer the sketch or code in our devices or microcontroller. Flame sensors used to detect fires. It has sometimes 3 or 4 pins. Pin 1 is the VCC that is used to provide voltage. Second pin is the ground pin, and third pin is analog, and fourth pin is digital pin. The Blink is very widely used IoT application. With the help of Blink, we can complex very easily. Blink support Arduino, Raspberry Pi, and other types of microcontroller. Blink can be easily downloaded from Play Store. It is free of cost. Blink include Blink app. We can make, there is no need to write code. It is GUI, graphical user interface. You just use drag and drop and button and make your app according to your own choice. Blink server is used for the communication. We can use the Blink server. We can make our Blink cloud. And third one, the setup Blink app is that after downloading the Blink app, you can log in with your email or Facebook account. After login, you can click on the create new project, and after create new project, you can give the name to your project like fire intimation system or add fire intimation system. Select the device that is node MCU and select the connection type Wi-Fi. And then you can select the create button. Then you have the auth code. That auth code is sent mailed to your email address, and that is used in your project. Circuit flame sensor have 3 pins: D0, ground, and VCC, and node MCU. The D0 pin is connected to the D1, ground pin is connected to the node and ground pin, and VCC is connected to the MCU 5-volt pins. The block diagram that the flame sensor is connected to the node MCU ESP8266 Wi-Fi module. The ESP8266 Wi-Fi module is connected through the gateway or router, and our mobile application, our mobile phones is also connected with the router or gateway to the ESP8266 Wi-Fi module. The system works as flame sensor send alert to the node MCU ESP8266 module, and node MCU ESP8266 Wi-Fi module is programmed way that it will receive the alert from flame sensor. It will alert to the, it will trigger or send alert to the one mobile phone application in here. The next is remotely control fan lights and appliances with the help of node MCU. ESP8266 Wi-Fi module relays and services of the Blink app. We can also control over lights, fan, and appliances. Purpose node MCU, relay, jumper wires, and Blink apps are used. The digital circuit is node MCU and relay. The node MCU is connected to relays ground pin. MCU is connected to the VCC. The node MCU D1, D2, D3, and D4 pins connected to the relays in 1, in 2, in 3, in 4. And by this, you can control 4 up to 6 at a time. If you extend the relay like 4 channel, 8 channels, and 16 channels, then you can control up to 12 and 13 appliances at a time with this. For that purpose, you can see the block diagram that the relay is connected to node MCU ESP8266 Wi-Fi module, and node MCU ESP8266 Wi-Fi module is connected to the router or gateway. And with the relay, our appliances are connected. The node MCU is programmed such a way when the smartphone user turn on or turn off the buttons from their mobile phone, they can control the home appliances according to that. Security system major component of the smartphone. By installing security system, we can easily detect suspicious or unwanted movement. In traditional security system, we use CCTV cameras, which only record the video, does not give warning about the intruder. In this, we use the intruder detection system. When this system detects unwanted or suspicious movement, it will give alert or buzzer the alarm. Following equipment is required for the class of PIR motion sensor, Arduino board that is used as the microcontroller, buzzer, and jumper wires. Here is the circuit. The PR sensor is connected to Arduino. PR motion sensor VCC is connected to the 5-watt of the Arduino board. Output is connected to the output to the pin 3, and ground pin is connected to the ground pin. And buzzer S pin, that is the signal, is connected to the pin 9, and the minus pin is connected to the ground. And PR motion sensor is connected to Arduino board. When PR motion sensor Arduino board is programmed in such a way that when PR motion sensor detects suspicious activity, or it will send alert to Arduino board, and Arduino board trigger the send alert to the buzzer. Result and discussions after successfully implementation, all the results are successfully achieved. The conclusion is that the smartphone automation system that are available in the markets are expensive, so there is a need to build a system that is cost effective for the families of lower, middle, and lower middle class. The availability of the Arduino microcontroller. With the help of Arduino microcontroller, we can make a low-cost smartphone model effectively. With the presented model, the smartphone users can successfully control home appliances. They can also get alerts about the unwanted suspicious activity, and in safety system, in case of fire intimation system, the system detect the fire and intimate us time. Thank you for me.
Thank you very much for your presentation. Do you have any question? Comments or remarks, feedback? No question? Thanks again for your presentation.
Thank you. Thank you.
Next speaker is Jedediah Peterson. The title of the talk is Gesture Control Robotic REMM Utilizing OpenCV.
Hello.
Yes.
Shall I go ahead and start sharing my presentation now then?
Okay.
Can you see the presentation, please?
Yes, yes, yes.
All right.
Okay.
Thank you everyone for being here. My presentation is a gesture-controlled robotic arm utilizing OpenCV. I've 3D printed my own robotic arm for this. I did not design it, but I did successfully 3D print it, and I used stepper motors, or servo motors, I'm sorry, to control movements. The reason what I'm going to talk about today is typical human-computer interface interactions, my system overview. I'm going to give you a flow chart that shows how I process my images, a couple of my methods that I use, what my project doesn't successfully do, and what it does do. And then I have a short video presentation at the end of it that shows my arm moving. So typical human-computer interactions for gesture recognition are two separate categories, either data glove collection or computer vision. Data gloves are extremely highly accurate, but they do have a few drawbacks that they can be cumbersome to wear for long periods of time. They do have a little bit of associated additional cost. If they wanted to be wireless, they need those Bluetooth RF chips, which are now a little bit cheaper, but they need a battery support system. If they're a wired glove, you lose mobility. They also need a lot more sensors to be able to determine things that are the movements of the hand. With computer vision applications for gesture recognition, we have various degrees of success depending upon the camera arrangements and the type of cameras that are used. But as the camera technology is ever increasing, we decrease the cost of these cameras that will be available. I've used OpenCV as in this project, it is an open source computer vision library platform for Python and C++. Great thing about open source products is that they're free, so you can port those to different applications. One of the drawbacks for using computer vision versus the data glove is doing image processing takes a little bit more computational effort. So if you want to do it in real time, you have to really optimize your code. These are two examples of data glove examples. We've got the Sarcos Guardian GT robot, and you can see that the man that's controlling this robotic arm, he's got these great big massive data gloves on that they measure all of his movement. Very highly accurate, but you can imagine that's not very portable. And over here on the right-hand side, we've got the Shadow Robot Company's dexterous arm using the Haptic X control device. And you can see that the Haptic X control device has got this big old cable coming off of it. Even though it's very accurate at controlling the robotic arm, it is not very portable. You can't move around a whole lot with it. One really cool thing about the Shadow Robot Company, though, is they do have a robotic arm going to the ISS shortly. Hopefully with computer vision, we can get rid of the need for these larger components, and shipping control devices to isolated locations like the International Space Station will become a lot cheaper. My robotic arm and the system overview here. So basically I have a very low cost camera. I use a USB 2.0 webcam that is inherently installed on my computer that I'm using right now to capture my hand gestures. I do image processing on my computer, which supports an Intel i7 processor. I transmit wirelessly over a wireless network to my Raspberry Pi. Communication is using TCP/IP socket protocols, and then I tell the robot arm which ways to move. The image processing, there is a lot going on here. So when you capture the image, you got to do a load of processes to extract key features from your hands. I'm going to cover some of these in a couple of slides and explain why some of these are very important. So the first step is you apply a Gaussian blur. This gets rid of really harsh edges and allows the image to be prepared for further stages of image processing. Then I convert everything from blue, green, red color scheme into an HSV, and I apply a threshold detection. The threshold detection turns it into a black and white image so that I can grab contours from the image. But when I threshold detect, I also have some inconsistencies left over that are detected throughout the image. And you can see that if by the sleeve on my arm here that has just been detected within threshold. So the step to clean that up a bit is called morphological opening and closing, and this is conducted in pairs. You close the image down, then you open the image, then you open the image a second time, and then you close it again. And in the bottom picture sequence of pictures here, you can see that it works at some matrix sizes, but if the image has too many blemishes in it, it can't completely strengthen the image by smoothing out all the edges. The next step is the edge detection. So you want to determine where your hand is, and I basically sort it by black and white pixels. But these images are often not very smooth because of dynamic lighting issues. So I search for the largest contour, assuming that that is the hand. Then extracting one important key feature is the center of the hand. You need to determine where it is for my system so that you can move the hand in 3D space. To do this, I compared 3 different methods of a minimum enclosing circle, rectangle, and the actual centroid. And I found that a minimum enclosing rectangle represented the hand center very stably and very accurately. The image in the green is the green contour, and the green circle are the center of the hand, and on the image on the right hand side, we can see a standard deviation of how the centroid of that contour changes over time. So stabilizing that for a controlled device is very necessary. Then we need to extract where our tips of our fingers are and where our interdigital folds are. This is done by creating a Hall convex around the contour of the hand and then finding the Hall points and the Hall defects. The defects are the largest, the furthest distance from the Hall, the convex Hall to the contour. And we can see that on the image on the left, those are represented by the green dots. And on the image on the right, my process finds those point locations on the contour, and I've successfully highlighted them. This is important for determining whether the hand is fully open or fully closed. Rotating the wrist. I experimented with a couple of methods of trying to figure out the best way to rotate the wrist. Here we can see on the left-hand side that I have an unstable first attempt. And on the right-hand side, I've got a much more stable that I average fingertip vectors over a period of time, and it creates a more stable wrist rotation. To control movements in the lateral or horizontal vertical directions, I've employed a quadrant control where I do a series of tests and then bit manipulation to tell the robot arm, yes, you can move left, yes, you can move right, no, don't move. And you can see that I've got color-coded quadrants here to enable or disable different bits. Achievements that I have made with this project is that the robotic arm is completely wireless. It can move around into different locations, or the host application can move. So I don't need to be a set distance as long as I'm communicating over top of this wireless local area network. I've got a hand gesture recognition range from 0.3 meters to 1 meter, and that it operates in real time. The one thing that the system doesn't do is it still needs calibrated for your hand color. It can only recognize one hand at a time. Background lighting and dynamic lighting still causes an issue. Individual finger manipulation is not possible, but it could be possible if we looked at the contours and we broke them down into smaller pieces and we provided interpolation and figured out how to find the maximum of the quadratic from that interpolation. But that would need to be profiled to see if it can be done in real time. In conclusion, this is a viable method of controlling robotic arms, but we need further development. And I just have a short video demonstration of me moving the arm around, closing the hand and opening it. The processor that I used here was a Raspberry Pi, which does not like PWM control very well. So it was very difficult to get these servo motors working all at the same time. Thank you for listening, and a special thanks to Dr. Stephen Boll and Dr. Kevin Webb for supporting this publication. Thank you very much.
Thank you very much for your nice presentation. Do you have any question or remark or comments, feedback? No question. So everything is obvious. Thanks again for your presentation. The last speaker of this session is Daniel Slavov. The title of the talk is Automated Control of Pasteurizations in Wine Production.
Hello, can you hear me?
Right? Yes. Yes.
Okay. I'll share my screen now.
Okay. Yes.
Okay, so I am Daniel Slavov, and together with my colleague Vladimir Hristov, we made this report describing automated control of pasteurization system. Okay. We are from the Technical University of Sofia, located in Bulgaria. So in food and beverage industry, pasteurization is used for decontamination and extending the product life of the products. And several types exist, which differ by their temperature value and time duration at which the temperature is maintained over the product. Most commonly used nowadays are high temperature short time and higher heat shorter time techniques, which heat up the product from 70 to 100 degrees and for a different time, less than a second to several seconds, less than 1 minute. For wine processing, the temperature needs to be below 100 degrees in order to maintain the wine quality, and it aims to destroying unwanted microorganisms, while at the same time it doesn't improve the quality, but it aims to not to worsen it. As with the techniques, there are different pasteurizers, but most commonly used and with the best thermotechnical characteristics are pipe flow or laminar flow pasteurizers, and such one is used in our work. Here there are 3 sections. If I may show you with my pointer. The middle section is called regenerative section. Here the left one is cooling section, and the right one is pasteurization section. So from the raw wine enters in the regenerative section, where it exchanges some heat with already pasteurized wine, which flows in the opposite direction here. And the raw wine heatens up to 50 degrees, depending on the application, but let's say 50 degrees. Then it enters the pasteurization section here, where it exchanges heat, this time with the heat carrier, which is hot water, and heatens up to, in our work, to 95 degrees Celsius. Okay, then it enters a containment vessel where some cooling of the already pasteurized wine happens, so it lowers its temperature to some extent, enters again in the regenerative section when heatens up newly coming raw wine, after which in the cooling section, in the cooling section, the wine gets cooled down to the desirable exit temperature, for example, 20 degrees. Interacting with the cold carrier, which is iced water with a temperature around 1 degree Celsius. Wine pasteurization installations can be regarded as automation objects with this input and output dimensions, as you can see on the slide. In our work, for controllable dimension or parameter is chosen the pasteurization temperature at which the wine exits the pasteurizator, the heat exchanger. For control impact is chosen the flow rate of the primary heat carrier, and most of the interferences or disturbances apply. In the wine processing, a specific disturbance is deposition of wine precipitates on the surface of the heat exchanger, which could be mitigated with proper washing of the system. This is the key diagram of the automated system. So we have here the raw wine enters here at the entry point. It fills up the VCL. This is a buffer vessel. Here is the pasteurizer, heat exchanger number 1. So the normal flow of the wine, if everything is okay, is from the entry through the buffer vessel, through the product pump 102, enters the regenerative section as described before, then the pasteurization section, and exits the pasteurizer. If the temperature measured here is accepted, in the accepted range, the wine goes to the containment vessel, which is in our case several pipes where it cools down to the environment, to the atmosphere. Then the wine again enters the regenerative section, the cooling section, and exits cooled down to the desired temperature, and then goes to a filling machine where it can be filled in bottles or as desirable. So we here control the pasteurization temperature, which is measured by this temperature sensor. And if it differs from the target value, this valve changes its position, which controls the steam flow. The steam is our primary heat carrier. So when we adjust this valve, more or less steam is entered to the system. It rises or lowers down the temperature of the second heat carrier, which is applied to the wine. So the wine temperature is controlled this way. For the implementation of our automation system, is used Siemens programmable logic controller S7. It is chosen for its compact design, large instruction set, and relatively affordable price. The software program is written with totally integrated automation portal from the same company using ladder logic, and also semantic human-machine interface is used. On the slide is present one of the comfort panels of the HMI with all the devices present in our system. Here is the control of the product pump 102, which was here right after the buffer vessel. So it is controlled by frequency regulator using a flow meter, and the flow rate of the wine is set by operator. For example, for 2000 liters per hour of wine, the pump needs to revolute with 3000 revolutions per minute. And here is a diagram of its control of its speed with proportional integral action. The control of the pasteurization temperature initially was tested with PI controller, PI action, but as you can see, there are some fluctuations of the temperature, and also a large continuous in duration overshoot. For a long time, the temperature remains above the set one in red, and the real one is in black, which overshoot needs to be avoided. So, secondly, we choose PID controller, and with determined optimal coefficients of the PID action, the shown control is achieved. As you can see, the overshoot here is much shorter, and temperature raise is smoother than on the previous regulator. There are no any fluctuations here in the temperature. So this controller was finally chosen for our system. In conclusion, the automation system can be applied for two of the most commonly used pasteurization techniques with different temperatures, which can be adjusted. Optimal regulator coefficients are determined for the temperature maintenance, and also, of course, the automated program would facilitate the work of the human operator and reduce the human error in this pasteurization process. And the system is always open for further improvement by adding additional features. Thank you very much for your attention.
Thank you very much for your presentation. Do you have any question or remarks, comments, feedback? No question? So everything is obvious. Thanks again for your presentation.
Thank you.
Dear Amir, can you hear me?
Yes, sure.
Yes, can you see me? I have opened my camera.
Sure, I can.
Yes,
see you.
okay. Can we discuss the issue about the paper with number 223? The paper appears in the program, and also we have the invitation letter, and we
well, actually, just a second. Okay.
Yes.
I have checked. I have installed that program from the main page of the conference, but I've never seen that there is such a paper whose number is 223, but it's not
223. The number is 223. If you go to the site now,
no problem. I have checked right now. No problem. But I have installed that program from the main page of the conference as every participant. It's not problem. But no problem. Then I can hear you, and you can present your paper. So right now I am taking a note that you can present your paper. So I have checked it. Anyone who participated this session,
I can send you all the documents.
So
I can send you all the documents, and we have also
no problem. I do believe you. I do believe you. So I'm ready to listen to you, and I'm ready
Thank you very much.
To your presentation. It's not problem for me, and anyone who has participated in this session then can listen to you or not, it depends on them. So I just want to express my pleasure to all participation to this specialization. So right now, now Fasolas will give the last presentation.
The presentation will be made by my colleague Nikolaos Kounalakis, as declared in the program.
Sure.
But Emir, I would like to ask your colleague Turgutos Seven about that, okay? And if I can send you an email to resolve this issue.
No problem.
Okay?
No problem.
Thank you
I
very
have
much.
taken the note. No problem. That I have taken the ID number of your paper, and you can present it.
Okay, thank you very much. Thank you very
Okay.
much, Amir.
Okay.
Thank you.
Sure.
Nikos, you can start your presentation, please.
Okay, so let me share my screen. Can you see it?
Right. We can see.
Okay, so I'm Nicholas. I'm a computer engineer from Control System and Robotics Laboratory of the Hellenic Mediterranean University in Crete. We are developing a tomato harvesting robot. The key points of these presentations will be the design of the end effector, the 3D vision system, the planning for a 6 degree of freedom manipulator arm, and some lab experiments with real plants. So there's a growing effort to incorporate robotics and automation technologies in the agriculture business. This has a few benefits, like standardization of the cultivation processes that lead to constant quantity and quality, smaller environmental footprint. It can replace some labor-intensive tasks that are also sometimes repetitive or boring, and it can reduce the cost, and it can give better control over the chemical environment in the greenhouse by managing the pesticides and the fertilizations. The challenges we faced while we were developing the robot was locating the cutting point on the pentacle, because it has some color similarities with plant leaves and branches. It has a variable shape and size, and we often see some occlusions. And the design of the gripper, which needs to be flexible enough to work in crowded areas, and it needs to be strong enough to be able to cut the pentacle. And during those procedures, we need to avoid damaging the crop or the fruits. And for that, we need precise detection and planning and awareness of the environment. Here we can see the materials we used. We used a differential drive robot with a movable platform. The platform can move vertically up and down, place the manipulator in the right spot to be able to work with the plant. We used RGBD cameras, a Jetson Nano embedded computing board for all the vision processing. We used two grippers powered by an air pressurizer. And in terms of software, we used ROS Melodic to incorporate all the sensors and the different parts. We used MoveIt to plan for the arm, and we used OpenCV as a framework to work with the images. Here we can see a closer look of the end effector. We can see the mount of the camera, the microprocessor, and here we can see the two grippers. The bottom one is used to secure the pentacle, and the top one is used to cut it. Here we can see the vision system. We had some specifications, like low tolerance for false positives, to avoid damaging the crop, and we need high localization precision to be able to guide the manipulator to the cut point. So we used the YOLO version 3 architecture and the DNN module from the OpenCV library to load the network. And we used CUDA to make things go faster. We built a dataset containing 728 images, including tomatoes and pentacles. And the key point here is how the annotation was made. As you can see in the picture to the right, the bounding box for the class pentacle is positioned in a way so that the center point coincides with the actual stem. And this is important because we'll be using this point to guide the manipulator, as we will see in the next slides. We evaluate the detector with the map metric with the intersection over union threshold at 50%, and we achieved a score of 77%. And as we can see here, for each class, the precision was 98% for class tomato and around 81% for the recall value was around 81%. And for the pentacle was 90 and 78. There is always a trade-off between the precision and recall in this type of detectors. We go with precision, with higher precision, and we can compensate for the lower recall value by a repetitive process during harvesting, and we'll also see that later in the slides. We also tested for localization precision. We increased the threshold of the IOU to 75%. And as we can see in the picture to the right, the class tomato remained unaffected, while the class pentacle had a lower score. This means that there are small deviations between the detected bounding boxes for this class and the ground truth bounding boxes. But we can also compensate for that by increasing the gap between the jaws of the grippers. And this is the pipeline we used. To the left, we can see a plant, and given the field of view of the camera, the distance from the plant and the height of the plant, we need 3 pictures to cover the whole plant. So we are starting our pipeline by deploying the manipulator to the position that corresponds to the bottom view with its end effector oriented parallel to its base. And from there, we capture an image and we pass it through the detector, and we get back the centers of the bounding boxes translated in 3D world coordinates by incorporating the depth map. And from there, we choose the one that is closest to the camera, and we relocate the manipulator to that point at a distance of about 20 centimeters while maintaining its orientation. From there, we capture a second image, this time looking for pentacles. Again, with the same procedure, we select the closest and relocate the manipulator at a distance of about 10 centimeters. Then we execute a linear motion to place the pentacle inside the gripper. And from there, we can cut it and deposit it to a container. The experiments, the purpose of the experiments was to evaluate the success rate of the above pipeline. A successful attempt was considered successful when the pentacle was located inside the jaws after the steps described above. And here we can see some successful attempts. We used 4 plants with and 15 tomato clusters with 2 to 4 tomatoes per cluster. The cutting stage was omitted to allow multiple attempts for each cluster from different positions and orientations. And after 6 to 8 attempts, the average success rate was around 65%, with clusters of fewer tomatoes having higher success rate and clusters with more tomatoes had lower success rates. We also classified failures to 3 categories, namely vision, gripper, and planner, to get a better understanding of what is causing these failures and focus our work to improve each one individually. Here we can see the result table. As we can see, this part is for clusters of 2 tomatoes, has a higher success rate, and it drops as the number of tomatoes increases. And here we can see the vision category for the failures included 5 failures. The planner category included 4 failures, and the gripper category included 16 failures. So let me explain a bit the categories. The vision category included false detections and camera depth inconsistencies, which can lead to inaccurate translation from the image plane to the 3D space. The gripper category involves collisions with either with the gripper with the pentacle or the gripper with the surroundings of the pentacle. And the planner category included failures that were associated with an ability of the used planner to generate or execute a feasible trajectory. Here I have a video for one attempt. Okay, let me refresh that. I don't know if you can see that. So that was the video. And some improvements we would like to make in the future is determine an appropriate orientation of the gripper or angle of attack based on the orientation of the pentacle. We need to make some patterns to avoid occlusions in case we detect a tomato in the current view, but we are unable to locate the pentacle. We can pivot around the point of interest to find an angle where the pentacle is visible. We will redesign the gripper to maximize its flexibility and minimize collisions. We should probably improve the accuracy of the detector for the class pentacle by incorporating more data. And we can test different path planning algorithms to find the one that has the fewer failures. And that was it. Thank you for your time. If you have any questions.
Thank you very much for your presentation. Do you have any question, comments, or remark? No question. Thanks again for your presentation.
Thank you.
Okay. So thank you very much for your participation to this session. So I'm ending this session right now. Thanks again for your participation to this international conference with your attending and presentations.